Hi everyone, Timothy Ferris here with a few words about time travel. And of course the first thing to be said is that we're all traveling through time in one direction, moving forward at a rate typically of about 1 second per second. We can slow that rate in various ways. They're all rather extreme. But if, for instance, you graduated in the future from some Space Cadet Academy and got prime assignments so that you were zooming around the universe at nearly light speed, not that that's necessarily even possible, when you came back for your 20th anniversary reunion, you'd find that not only had you had a more glamorous career than your classmates, but you were actually younger than they were, because during the time you spent at those high velocities, your time on board was moving more slowly than it was for your classmates back home. The American astronaut Mark Kelly, who spent, I think, about 500 days in space aboard the International Space Station, calculates that he wound up about 8 milliseconds younger than if he'd stayed back home on Earth. If you saw the film Interstellar, you may recall that the astronauts at one point go down to a planet orbiting a massive black hole. Space, and therefore time, space-time being the same entity, so warped in those conditions that a single hour on that planet was equal to 7 years in the outer universe. One wonders whether there are hobbit-like creatures living on such planets orbiting black holes here and there in the universe to whom the pace of time in the rest of the universe seems almost comically accelerated compared to what they would regard as normal. But when we talk about time travel, typically we're talking about travel into the past. Is it possible to build a time machine, as science fiction writers have often envisioned it, and use it to go back into the past and maybe change something for the better so that the present time when you come back you'll find is a happier time than it was before you interfered with its history? Now, there's no evidence for this. Stephen Hawking used to like to point out that if time travel were viable, our present day would be flooded by speculators coming back to place bets on the stock market. If, for instance, you lived in the year 2100 and time machines were available, you might want to travel back to, say, 1990 and buy shares in Apple for around 31 cents a piece, leave instructions to sell them in, say, 2022 for $173, put the proceeds into a trust fund account, return to the year 2100 and find that you had made quite a lot of money. We don't see that, and the artificial intelligence monitors that read stock market transactions would note such anomalies cropping up in something like the way that several Manhattan financial institutions identified Bernie Madoff as a fraud years before law enforcement caught up with him, simply because of the unlikeliness of placing so many bets that really did that well. So we might wonder, how come no one's visiting us from the future? Is it really not possible to travel into the past? That does appear to be the case, although there's a little loophole I'll get to at the end. And to discuss it, I'd like to look at the paradox of time travel through two lenses. First, that of classical science, as exemplified by Einstein's relativity theories, and secondly, in terms of quantum physics. The early science fiction accounts of time travel tended to see time as akin to a railroad track. That was the highest form of technology, circa 1880 to 1910 or so. And lots of people had enjoyed the experience of sitting in a comfortable chair and looking out the window to see the landscape gliding by at what had been unattainable speed. So the idea was that you would take a kind of railroad back in time and change something and then return to your present time and see how your efforts had worked out. But this line of thinking immediately runs into paradoxes. And to illustrate the paradoxical nature of linear time travel in a classical physics environment, let me take the example that people often talked about of going back in time and murdering Adolf Hitler before he could set off World War II with its catastrophic loss of some 50 to 70 million people killed in that conflict. could you avoid World War II if you had a time machine? Well, let's say you tried it. You decide that the ideal date is September 17th, 1900, the day that an 11-year-old Adolf Hitler first headed out on a walk in a country lane to get to the vocational school to which his father had decided he would go in Linz, Austria. Let's say you're an operative chosen because you have an Austrian background and you speak the language, you know the history. So you're dressed up to look like a contemporary in 1900. You're given a rifle that was available at the time so you can pass yourself off as a hunter if anyone asks any questions. And you hide there in the woods and you wait for a little 11-year-old Adolf to come along and you shoot him. That would be the idea. And then you'd return back home and see if the world was a better place for the lack of World War II. The trouble is that would have changed a lot of things. Suppose your parents had met because of the war. Now you wouldn't exist. Well, you make it more concrete. So you take the shot at little Adolf just as by chance he sees a rabbit scurrying by and veers off his path and see if he can't kick that rabbit. Your round goes past him down into the town, where as luck would have it, it strikes a 20-year-old postal worker, kills him, and he was your great-great-grandfather. Now, that's the grandfather paradox. You can't be there to carry out the assassination, so do you exist or not? That's the problem with linear time travel. If we look at time travel through the lens of quantum physics, however, some new opportunities open up, particularly in terms of what's known as the many worlds interpretation of quantum physics. This was an idea developed by a scholar named Hugh Everett and later extrapolated upon by Bryce DeWitt and others to try to resolve a central conceptual problem with quantum physics. It's not a scientific problem. Quantum physics works fine. It's a problem with what the implications are of the way we interpret the science. To understand the many worlds interpretation, let's go back to the basic paradox that afflicts efforts to understand some aspects of quantum physics in terms of our understanding of the world around us. Now, in a typical such experiment, and I've discussed these a little bit in some of the other lectures, you take a pure quantum system. This could be a set of photons, let's say, that you've chilled down and trapped in a little cold chamber. Any system that's settled into a single quantum identity. Because remember, particles are just one way that quantum fields express themselves. If you leave them alone, they'll settle into a coherent system that's neither particle nor wave. It's not interacting very much with anything around it. Now, the quantum rules state that you can learn as much as you want about one kind of information about a quantum system. I'll just call that A or B. Could be comparable to spin up or spin down. It doesn't really matter. It's a certain kind of information about this system. But if you do, you cannot then find out about another aspect which I'll call X and Y. Okay, so the more you know about A and B, the less you can know about X and Y. That's the Heisenberg uncertainty or indeterminacy principle. It simply expresses what is the quantum limit on the amount of information you can get out of an atom or any other quantum system. So let's say we try to evade this limit by doing an experiment that's actually been carried out many times, which you take this system and you send it to a splitter so that it goes out along typically 2 fiber optics channels to 2 observers, we'll call them Alice and Bob, who are far apart, 10 miles apart, let's say. And using their atomic clocks, they simultaneously interrogate the same system. So let's say Alice asks, is it 1 or 2? And gets an answer, it's 1, let's say. Bob, at the same moment, asks the system, is it A or B? And the system won't tell him because that would violate the Heisenberg principles. What it'll do is give him random results. And this is true even if they're so far apart that there has not been time for a signal traveling at the velocity of light to go from Alice to Bob. The usual issue raised here is how does the system know? How does it know that its been interrogated over here, so it can't give you an answer over there. In the normal interpretation of quantum physics, you say, okay, Alice made a measurement, and now Bob can't get any more information out of the system. But if Alice didn't make the measurement, Bob would be able to extract the information. So what happened to the information that we know was there? It was on its way to Bob. He was able to get it if the system hadn't been interrogated by Alice. Where did it go? In quantum mechanics, this violates a basic principle. Information follows the same rules as thermodynamics. Thermodynamics tells you that energy can be transformed but not obliterated, and it tells you that information can be degraded, but it cannot be removed entirely. So it seems as if there was something magical going on that would cause one aspect of the information to be attainable, but only at the expense of the other. What happened to the information that seemed to have disappeared? In the Copenhagen interpretation of quantum mechanics, you would say, well, the wave function collapsed, and you got this kind of information, but not that. It was lost in the collapse of the wave function. What Everett suggested was that the wave functions never collapse at all. All the information's really there. It's just that reality divides somehow every time such a measurement is made. And it doesn't have to be by humans. Any interaction of quantum fields will do. In a sense, you have split reality into one reality in which Alice gets her information and another reality in which Bob gets his information. And it looks to you as if the information were lost, but it isn't. It's just in a slightly different version of reality. Now, Everett never called this splitting. Bryce DeWitt and some other commentators introduced the term. And a lot of people didn't like the idea of the many worlds because it seemed so extravagant. As Stephen Hawking said to me once, we don't feel like we're splitting. But splitting wasn't really the idea. It's more like an interference pattern that you can imagine there are lots and lots of versions of reality like cards in a deck. And our path in time follows along a given route that is determined by all the quantum interactions that occur in our lived world, and that's true for every other observer everywhere else. The beauty of this interpretation is the entire universe then has only a single wave function, as you say in quantum mechanics, and everything else is just a derivative of this function. It portrays the universe as one entity rather than many, but that one entity contains an enormous number of variations on the world one lives in. At the time that it was proposed, one of the objections to the many worlds was that there just wasn't room for it. Where would all these universes exist, cheek to jowl, all these slightly different versions of reality? But that's no longer the case. Work in M-theory and other areas has shown that it's possible for the universe to contain an enormous variety of space-time manifolds, different kinds of space-time. The total amount of space to which a universal quantum wave function would have access is more than enough for the entire universe to be splitting zillions of times a second. But if we try to time travel into the past, even under the many worlds interpretation, we run into some problems. So let's say that the many worlds is right. You take your time machine, you travel back to Austria that day in 1900, and you manage to kill little Adolf Hitler and thus, let's say, avoid World War II. How do you get home? Find out what happened. Every event is constantly changing the reality around you. It doesn't look like that because your path is always one aspect of that change, so you don't see the world of the Bobs who got the information out of the system but look to you as if they didn't get the information. You have a splitting function in your future that is so vast that the chance of your getting back to where you departed in your time machine, in the year 2100 or whatever, is phenomenologically zero. You're just not going to do it. Maybe there's a way to do it. I suppose maybe there's a science fiction book that's been written on the idea of how would you surf your way back through these zillions of possibilities and get to the reality that you started from. But the lesson seems to be that if it were possible to travel into the past, you couldn't get home again. Are there such time travelers? No evidence of it, although you see fuzzy photos of what people think are someone looking at a cell phone on a beach 100 years ago or something like that. But if there are any time travelers visiting us from the future, they've made themselves mighty inconspicuous, and they're going to have to stay here. They can't go back. As the columnist Jim Bishop wrote back when I was a kid, nothing is as far away as 1 second ago. Thanks for listening. See you next time.